Okay, you can start.
Okay, great. Okay. Hello all and welcome back to the second session on description logics. So in the previous session, we looked at the context, right? So I talked about artificial intelligence and then knowledge representation and reasoning. And within that context, I talked about description logics as well. And um, so I also mentioned that this is a decidable fact of first order logic, and I gave a few examples of it. So we'll be starting off with the description logic syntax now and the various constructs that it supports, right? So um, that's what we'll be discussing in this particular session. So let's get started. So I briefly discussed this example, and I think I can just go over it again. So we can, since it's a subset of first order logic, we can easily convert any. So this is an axiom, right? This is the T. So we also looked at three types of axioms: the T box axiom, the A box axiom, and the R box axiom. So T box axioms are the T stands for terminology, right? Terminology. Right? So terminological knowledge. So that talks about the schema level or the abstract level relationships between the concepts. So something like, so you talk about person in the schema, but as part of the A box, A stands for assertion. So that's the assertional knowledge, right? So in the A box, you talk about the individual person, something like Mary, John, right, Raghava, and so on. So they are all instances of person. So the instance data makes up the A box, and R box consists of the uh, how different roles are related to each other. So R in R box stands for roles or relations, right? So for example, this is an R box. So has wife is a subproperty of has spouse. And this can, we also discussed in the morning that we can map this to sets and set theory. So you can take this as a set, and the instances of this particular concept are like the elements of the set. So John, so this is the name of the set, and the elements of the set would be John, Mary, Suresh, and so on, right? So those are the elements of this particular set. Okay, so now you can see the mapping or the translation. So this is the description logic syntax, and this is the equivalent first order logic statement, right? And it's the same for the rules. So subset or subclass relationship maps to the implication, and there's the equivalence which can be mapped to by implication, right? So this is the X has y, that implies that X has spouse y. Okay. So let us look into the other constructs of description logics. So we have the quantifiers similar to the ones we have, I mean, in first order logic, because like I said, it's anyway a subset. And there are other things also, right? We'll look at all these different constructs and properties in this session. Okay, so there are two quantifiers: the for all quantifier and then the there exists quantifier. For all, so this indicates that there is an exam concept that is related to the professor concept through the as examiner relationship. Now there's also the quantification on top of the way it is related. Exam and professor are related. So so this indicates that all examiners of an exam must be professors. So if there is an examiner for a particular exam, that examiner has to be a professor, right? But it can also be a case that, so it also includes the zero case. That means this also includes those exams that do not have any exam. So this includes two cases: when there are no exams, true, and if all the examiners of an exam are professors, then also this is true, right? So that's how we can interpret this. Okay, so this is the happy person is someone whose all children are happy or happy persons. So if every child of a person is happy, then that in turn means that the person is also happy. And this also includes, similar to this case, this also includes a childless person, and they are also happy. Right, that's the for all case. That means every, so if you think of it in terms of sets, so let's say this is one set which has multiple elements, and this is the exam set, and there is one more professor set. And if the exam set, if an element in the exam set is connected to the professor set, then sorry, if the element is connected through the has examiner set, then it should be in the professor. It should land up in the professor set. So that's what this means. Okay, the other quantifier is there exists. So this there exists, or you can also read it as at least one. And this indicates that every exam must have at least one examiner who is a professor, which is different from this one. So this indicates that all examiners should have must be professors. This one, at least one examiner should be a professor, right? So for example, let's say there's an exam, a math exam, and that has 3 examiners. Now, if at least one professor is an examiner, sorry, if one examiner is a professor, then we are happy if this is the quantifier. But if that's not the case, then, but in this case, you should have all the examiners as professors, right? So that's the difference. And here, this no examiner case does not exist because it's an at least one, right? So there should be at least one element in this one which is connected through the has examiner to the professor. So that's the 2 quantifiers, existential quantifier and universal quantifier. Okay, so there are also some special classes and properties. So let's say there is something called the T symbol, which stands for top. Top is the super concept for all concepts, and that means it's the parent concept for everything. So you can also treat it as the God concept, right? Like it's the parent for everything. And in terms of the set theory, again, this is equivalent to the mu set, which is the set of all sets, right? And the contradiction or the opposite of that one is the bottom concept. Bottom concept is equivalent to the null set, so it doesn't contain anything. So top concept is the super concept for all, and bottom is the sub concept for every concept. So those are and they are negations of each other. And similarly, we have the U, which is the top property. That means it's a super property for every property, and then there's the empty property, which contains nothing. Okay, so these are the special classes and properties. Okay, then we have these constructors. Any questions so far? Okay, so let's move ahead. So we have the intersection or conjunction, right? So we can start with an example. So this is same as the set intersection. Mother is exactly those who are female and a parent. That means there's an intersection. So they are female intersected with parent. Right? Union or disjunction. So parent is someone who is a mother or a father. So either a mother or a father. And you have the negation. Unmarried woman is exactly those who are a woman and not married. Right? So that's the so here you have the negation of top is bottom and vice versa, and it's the same here. Negation of U is empty. Okay. So you can also so you can start using top and bottom in this way. So top is union of male and female. Okay, you have now you can have one more, which is other gender. So it's male, female, and other gender, I guess. So that becomes the top. And then you have this one, which is it's like the tautology, right? This is always true. This is equivalent. This is same as C or not C, which is always true. So either C is true or not C is true, and the distinction between them is always true. Okay, this implies the disjunction. Sorry, the disjointness, right? So male and female, the intersection of that should always be a null set. That means that there is nothing that is common between the male concept and the female concept. So they are disjoint with each other. Right? That's what this means. Nobody can be both a male and female at the same time. And this is the contradiction, right? So C and not C is always false, and that's what this indicates. So we also have the something called the nominals. So nominals are nothing but it's a concept that has exactly one instance, right? Like a singleton. So in object-oriented programming, we have the singleton class. We can have a singleton class where the class has exactly one instance. So this is very similar to that. So you have a class that has only one instance. So they can be used to create these closed concepts. So where you can exactly specify what should be instances. So let's say in other cases, right? Let's say you have mail concept. Now you cannot exactly specify who are all the instances or what are all the instances that make up this concept, because there are several mails in this world. So you can't keep listing each mail one by one, right? But if there are less number of instances, let's say a weekday or a weekend. So weekend can only have Saturday and a Sunday, right? There cannot be more instances than that. And same is the case with the weekday. There can only be 5 instances for a weekday. So if that is the case, that means you are closing the number of instances that can be associated with the concept. You can use these nominals, and the way we make use of it is by just using these curly braces and just listing out all the individuals, right? So for example, you have this my birthday guest class, and you are sure that your birthday guest will only be Bill, John, and May, and nobody else. And in order to avoid the case, you want to explicitly state that they are all different. So because of the no unique name assumption, you can add this as well. So the intersection of Bill, John, and Mary is empty. That means there is nothing in common, and they are different from each other, right? Okay. So let's go ahead with the cardinality restrictions. Any questions so far?
Yes, hi. So, can you please go back to the slide where you introduced quantifiers?
Yeah, sure. Okay, this one.
Yes.
This is
so,
only slide. Yeah,
yes. So for example, in the first sentence, exam is a subset of for all has examiner one. So how would I translate this into the first order language? How would I write it?
okay. So it's a sort of a combination of. Okay, I don't have a tablet with me, so we'll have to do it step by step, right? So for example, so the subset or the sub concept or subclass, this is a subclass symbol, is translated to the implication. Okay, now okay, and then there's already a for all symbol. So you say that has examiner is a binary predicate, right? So I mean any predicate or a role here, it has the role is a binary predicate. So here now x, let's say if x has y, so we are indicating that we need to add the statement that x is coming from exam and y is coming from professor. So you add that part.
Okay, so
there is an x
there, right?
Yeah, exam is a concept and professor is another concept. So you say that there is such an x and a y such that x is, so exam of x, you need to write exam of x similar to women of x.
Okay.
And then there is the implication for the subclass symbol, and then you state that has examiner of x comma y, and on top of that you should add that the y is from professor, or y should be associated with professor.
Okay, so is it like for all x, then we open a bracket, exam x arrow, for all has examiner x y, and
For all x and for all
y.
y, both are. Yeah,
Okay,
but go on.
probably try to write it down once, and in the end maybe I can
Sure, sure.
ask you.
Okay.
Thanks.
Okay. Okay. Any other question before I move?
Yeah, this nominal is defined only for finite number of instances, right? When we have only finite number of instances.
Okay, your voice is not clear. I couldn't get the question.
Okay. About the last part that you said about the finite number of instances, only you can define this nominal thing, right?
Yeah, right. Okay, this one. True. So what's the
Okay.
question?
So it's, I was just asking, it is not for infinite, it's only if it is finite number of
True.
instances
Yeah,
we
if
can
it is
define.
finite, and then it's also very less in number. It can't, because we can't sit and enumerate all the possible individuals. So something that is fixed. Say, let's say like the weekend example that I gave, the months in the calendar year. So those are only 12. Uh,
Uh,
weekdays, weekends, and in this
Suppose it
case.
is like a range of values, for example, 1 to 10 or 1 to 100. Like,
So you will have to enumerate each one of them. But
oh,
generally,
okay.
it's say, okay, so unless you have something additional information apart from just a number, right? For say, for example, temperature. Temperature will have a number, a value, and a unit associated. So unless that's the case, I generally just the numbers are not made as instances. There has to be some additional information associated. But yeah, so just to answer the question, yeah, you will have to enumerate each one of them. And to make it very safe and explicit, you should also add this, that all of them are disjoint with each other.
Unique, okay.
Yeah, they are unique. Okay, so let's go ahead with the cardinality restrictions. So these allow us to restrict. So okay, you can. So after we go over this, we can also convert the there exists into one of these, right? So we'll look into it. So this will allow us to restrict the number of individuals that can be connected to each other. So let's say there is an exam, and you want to say that exam has at least 2 examiners. Every exam should have at least 2 examiners, right? So we don't care who the examiner is, but there should be an examiner, at least 2 examiners. And this one says that exam can have at most 2 examiners, so that means it's 0, 1, or 2. Right? So and we also have the exact symbol. If you put an equal to, then that's the exact, which is same as at least 2 and at most 2. At least 2 intersection with at most 2, that gives you exactly 2. So this is the general form, right? So you have greater than or equal to n. N indicates the numeric number, numeric value, and the relation R. So these are the regular cardinality restrictions where you don't specify the class to which this should be related to. So in some sense, you don't care for what there is, right? So it can be any examiner. You're not specifying the type of examiner. So in qualified cardinality restrictions, you also specify that. So along with the cardinality, you also specify the type to which this belongs to. So for example, here we say that every exam should have at least 2 examiners and they should be professors. So earlier we saw the unqualified cardinality expressions where you don't necessarily care what is on the what follows the relation or role. So it can be a top in general, but here you specify it explicitly. So in the at least one case, here it should be 1 in the existential quantifier. So for existential quantifier, you can write the same thing using cardinality restrictions by replacing 2 with 1. So every exam should have at least 1 examiner who is a professor, right? So you can do that. Okay. So there's the concept of inverse roles where the direction is reversed. So for example, you have A has son B, and then B is the son of A, and both are same. So You can specify that using this one. So has son is equivalent to son of, and specify the inverse here. So if A has parent B, then that means that B has child A, right? So you can, again, these two are inverses of each other. So all these things can be used to answer these questions, right? So for example, you stated in your knowledge base that A has parent B, but if someone asks you question is who are the children of A, or how many children does A has, then you will be stuck, right? Because you talked everything in terms of the parents. So if you have these kinds of inverse roles, then it becomes easier to answer different types of questions. Okay, so for each role that we define, we can associate certain characteristics to it. So one is the transitivity characteristic. So which I guess so I guess all of you should be familiar with these characteristics, right? So you have A is related to B through the R relationship, and B is also related to C through R. Then if you say that these are transitive, R is transitive, then we can make this inference that R is also related to A and C, right? But again, you will have to explicitly specify that R is transitive. Then this can be inferred. So an example is has ancestor, right? So if A has ancestor B and B has ancestor C, and if you make has ancestor as a transitive property, then you can infer that A has ancestor C. Okay, symmetric, they are related in either direction. So A is related to B through R, and B is also related to A by R. Has spouse is the example. Asymmetry doesn't allow that bidirectional relationship. So if A is related to B through R, then it is not the case that B is related to A through R. Right? Example is has child. So if A has child B, then definitely it's not true that B has child A, right? So that's the case. Okay, then we also have the reflexive and irreflexive properties, which I think you would be familiar again as well. So A is related to itself through the R rule. So has relative is a reflexive property. A has relative A. Like that means they are related to themselves. Irreflexive indicates that the self relation is not possible, right? So parent of is not a is irreflexive. So A cannot be the parent of A. So that's the irreflexive. Okay. So this could probably new, which is functional and inverse function. So functional, so if you say that R is functional property, then this is what it means, right? So A is related to B through R, and A is related to C through R, then that means B is same as R. So if you make R to be functional, and if these two hold, then you can automatically infer that B is same as C. So for example, has husband, right? So if A has husband B and A has husband C, and if we say that has husband is functional, that means a person can have only one husband, then we can say that B and C are same. That means they are alias names of each other, right? So for example, A has husband John and A has husband Jim, right? And if has husband is functional, then John is same as Jim. That's what you can infer. And this is the description logic equivalent. Okay, inverse functional. So inverse functional again, if A has husband B and C has husband B, then this means that A is same as C. Right? So that's the inverse function. So you are just focusing on the first argument or relation. And this is how you specify this in description logics. Okay, any questions? Okay, so yeah, let's go ahead. So we'll now look at a couple of description logics, right? So some of the examples. So here, so far we have looked at some of the constructs. Now we can put together some of the constructs that we defined, and then we can create these description logics. And the good thing with the naming of these description logics is that they are based on the constructs that they support, right? So here ALC is supposed to be one of the smallest and well-known or well-used sort of description logic, at least to get started, right? So this is supposed to be the simplest one, or one of the simpler ones. Okay, so you have ALC, which stands for attributive logic with complement. And like I said, it's considered to be one of the most fundamental ones. So you represent the individuals using small letters, ABC, the atomic classes using capital letters, and role names are also represented using the capital letters. So it supports these kinds of statements. So C is equivalent to D or C is subclass of D. That's the T box statement that it supports. In A box, it supports class assertion and role assertion. So that means A is of type C. A is related to B through R. And these are the constructs that it supports. So so it supports simple classes, atomic classes, top, bottom, negation, intersection, union, and the two quantifiers for all and existence. And this is an example of ALC. So you have A intersection B, subclass of this whole thing, right? So this is in ALC. So you can start with this one and construct this entire thing using this the sort of the rule that we just said. So ALC has support for these concepts and the constructs. No, sorry. Okay, like I said, the naming is quite logical in the sense that we use letters that indicate the language constructs. So S is used for ALC plus role transitivity. H is used for role hierarchies. That includes simple role inclusions. O is for nominals, I is for inverse roles, N is for cardinality restrictions, and Q is the qualified cardinality restrictions. Okay, so there are more, right? So you also have D for data types, F is for role functionality, and R is for the generalized role inclusion activities, which is property chains. E is for the existentials. Right? Okay, so those are the letters and their corresponding constructs. So, for example, one description logic is showing. It is called as showing D. D indicates data type, and as we discussed, S indicates ALC plus transitivity. H indicates role hierarchy, right? That's what, yeah, role hierarchies. O indicates the nominal, I indicates the inverse, and indicates the cardinality constraints. Yeah, N is the cardinality constraints, and Q is the, so here we have Q. Q is the qualified cardinality constraints. Is that okay so far? Okay, so let's go ahead.
So we have, so D denotes data types, right? So how do we, where are the data types in the logic?
Okay, right.
So
Okay,
I
so
think
we have so for example, we can have concepts like string, double, float, and positive number, negative number, and so on, right? So these are some of the concepts, and now they are like, they act as the data type. So if you look at the data types that are used in the ontologies, then they are borrowed from the XML data types. We call it XSD, right? It's XSD data types. But yeah, we can treat it as concepts like string, non-positive number, uh, real number, date. So these are all concepts and data types as well, and the instances of which are what are yeah, we can create an instance and say that these of type D or data sorry, of type date. I know, does that help?
yes.
Okay, okay.
Thanks.
Okay. So there is always a trade-off between expressivity and complexity. So now what do you mean by expressivity, right? So different description logics depending on the constructs they support. They are either so the expressivity can vary. So for example, if there's a description logic that supports only S, so that means it's just ALC plus role transitivity, right? So it doesn't support cardinalities, inverse roles, and so on. So that means it's less expressive than the other case where there's a description logic that supports all these things. So the more expressive the description logic is, the higher is the complexity, and the lower the it is expressive, the lower is the reasoning complexity, right? So there's a trade-off between these two, and we have listed the reasoning complexities here. So ALCs of exponential time, and so on, so on and so forth, and until you get here, right? Shine is non-deterministic exponential, and N2 would be double non-deterministic exponential. So these are all, in some sense, if you look at this, these are all disheartening, right? So you don't want to work with logics or in general any computing related stuff that is not polynomial in time. And exponential, if it is a large ontology, it will take a lot of time. So something had to be done, and we don't discuss it. Okay, I think we'll discuss it in the OWL. So they proposed a subset of these things. So let's say maybe take a subset of ALC itself, and then use it for creating these knowledge bases. And the way these are pronounced is you just pronounce it the way it is written, right? So this is Shik, Shock, Shio, Shine, Shoik, and Shroik, right? So this is Shoik, Shoik, and this is Shroik, right? And as you can probably guess, this is the most expressive of all, right? Because it has everything that we discussed so far, which is transitivity, role hierarchies. This is the what's it called? The nominal. I is inverse role, and Q is the qualified pattern. Right? Any question on this one? Okay. So at the end of every slide set, I include these references. So if you want to learn more about the concepts that were discussed in the slide, you can click on this, and then most of them are research papers, some of them are textbooks. So you can get some more material by going over the references. Right? Any questions so far? So let me just switch over to this one. Okay, so I'll change the date and the. So these are part of my class lecture sites, but I'll change them. I'll change the initial dates later on, right? Okay. Any questions before we go ahead? So I'll briefly introduce web ontology language, and then in tomorrow we can create these ontologies together. So okay, let me just give you this before I forget. So search for Protege Stanford, right? And then you can download this and keep it handy, so that we can use this to build the ontologies tomorrow, right? So you download it, and then it's just a unzipping of the zip file. So it should be pretty straightforward, right? And we'll be using this Protege. So maybe I can even paste this link in the chat. It's helpful. Okay, that's the link. Okay, right. So yeah, we'll be using the web ontology language to create these ontologies. So now what is the link between web ontology language and description logics, right? So you will notice that web ontology language is built on top of description logic. So description logics is the formal underpinning for OWL. So in short, it is called as OWL. Okay, so let's get started with OWL. So again, OWL is a knowledge representation language similar to description logics, except that it is used to build ontologies. And OWL 2 is the latest version. So earlier it was OWL 1, and that has been replaced with OWL 2. And OWL 2 is more importantly a W3C standard. W3C stands for World Wide Web Consortium. So are there any other standards that you are aware of that has come from W3C? Maybe you can write the answer in the chat. So this is a standard that's used in our day-to-day life, right? So whenever you are browsing, you are using this W3 standard. No, any guesses? Okay, so it's HTML. So HTML is a W3 standard, and okay, since we are talking of standardization, we can as well discuss the advantages, right? So the advantages of having any standard is that any implementation that is based on standard will have similar inputs and outputs. So for example, we can take the HTML itself. So there are several browsers like Firefox, Chrome, Internet Explorer, and so on. Right? So there are multiple different browsers. So all the browsers should be able to render the piece of text in the same way, with or without HTML tag. So let's say if there's a HTML tag, let's say there's a HTML tag called bold, which will make the text to be darker in color, right? Bold color. So if Chrome and Firefox stick to the same standard and implement it in the same way, then the text should be rendered the same in both the browsers. Right? So that's the advantage of standardization. So you can start using any ontology editor or any of the ontology related tools, because all of them will stick to the same format. So that's the advantage of having something as a standard, right? Okay, so we have three types of entities, similar to the three types that we saw in description logic. So in description logics, it's concept, property, and individual only, right? So it's instance, I guess, which is individual. Okay. So classes are same as concept. So they are used to group together the individuals that belong to the same class. So for example, you can have employee, student, father, and mother. Right? Properties are the binary predicate, and individuals are the instances or the constants. Right? So Mary is an instance of woman, Julie is an instance of parent. And the important thing is that all these entities are uniquely identified using what is called as an IRI. IRI stands for Internationalized Resource Identifier. So we'll talk about the different identifiers here, but there are multiple different types, right? But for the ontologies and semantic web in general, we'll only be using IRI. Okay, let me again take a pause here, and if there are any questions, let me know. Okay, so let's go ahead. Maybe we'll discuss a few more of these OWL related syntax and semantics, and then we can come back to more to it. Okay, so you are all familiar with, I'm assuming all of you are familiar with URL, which stands for Uniform Resource Locator. So do remember that everything in the ontologies and RDF, right? So they have a IRI. So every concept has an IRI. So all these three things. Every class has an IRI. Every property has an IRI, and every individual has an IRI. right? So they want to uniquely identify each one of them. So now the next question is, what is an IRI? So in order to know the IRI, we'll start with a URL, right? So URL is something that is browsable. So you can put it in the web browser and then expect some sort of response where it indicates a human readable description, right? So for example, if you put google.com, so something that can be rendered on the web page and which is human friendly will show up. So it's a mechanism to identify a web resource, but which is also human readable. Okay. URN is again very similar in the sense that it can be used as an identifier, but it's not browsable. So you cannot browse a URN. So something like the ISBN of a book is an example of a URN because it's used to uniquely identify a book based on a series of numbers, right? Okay, then you have URI, which is which supports more characters. So it supports ASCII encoding, but again, it is used for identifying a web resource, except that it need not be browsable again. So if you put a URN in the browser, it need not be resolved to anything in particular. Right, that's the URI. And then we finally, sorry, that's the URI. We finally come to IRI. So the only difference between URI and IRI is the encoding scheme. In URIs, you have the ASCII encoding, and in the IRIs, we have the universal character set, UTF_8. Right. Other than that, everything is the same. So with the UTF-8 or the universal character encoding, the advantage is that you can add more and more characters, right? So for example, you can have an accent on top of it. This is the umlaut, it's the O umlaut. So all these are special characters which are possible in IRIs, right? So these are the 4 forms of identifiers. And in the semantic web and in ontologies and RDF and in general in the semantic web space, we use IRIs. That means it follows the universal character set, UTF-8. So let's see certain examples, naming conventions and certain examples. So the naming conventions are same as for description logics, right? You follow the upper camel case for classes, and for relations or roles or properties, we follow the lower camel case, and for individuals also we follow the lower camel case. Okay. So this is the OWL syntax. So we won't go into the syntax in depth, right? Because it will be taken care of by the tool, the Protege tool. So we'll only look at the high level version. So there are different ways of serializing an OWL. So once you construct an OWL, it has to be saved in a file, right? So how do you save it in a file? In order to save it in a file, you need to have a certain syntax. So these are the syntax that are available. So you have function style syntax, RDF XML, OWL XML, and Manchester syntax, right? So in the subsequent slides, we'll be looking at one of these syntaxes because okay, we can either follow the description logic syntax or the OWL syntax. So since we are looking at OWL, we'll be following the OWL syntax, but I think there are also examples using description logics. Or maybe let's check. So we follow functional side syntax because it's the most human friendly. Right? Okay, so this is an example of a functional syntax. So you declare that person is a class using this declaration. Mary is a named individual. So you don't have to associate Mary with any class. So you can just leave it as it is as an individual, right? But then when you assert it, you are converting this to an instance. So now Mary is an instance of person, Mary is an instance of woman. And the object property assertion states that John has wife Mary. Right, and these are all called as axioms, which we have already looked at. So you have the T box axiom, A box axiom, R box axioms. right? So you can also have complex expressions or atomic classes. So if it is something like simple one, so you have class property and individual, and they are all connected to each other. But one of the classes is slightly more complex, right? So for example, you have a subclass of B intersection. In the parenthesis, you have D union E or something. So that's slightly more complex. But using all these things, the constructors that we have discussed so far, and then the syntax that we have discussed so far, we can capture the knowledge of a particular domain, right, in the form of axioms. And axioms are nothing but the facts related to that domain. Okay. So I think, I don't know, should I go ahead with a few more slides? So maybe I'll pause. So any questions so far?
Yes, so how would we, can you go back to the previous slide? Yes.
Yes.
So how do we declare an object property? We would write declaration, and how would we declare an object property? Like has wife, if you want to, for example, we have declared person is a class, right?
Right.
So if supposedly one wants to declare has wife in the starting. So
Okay. So I'm assuming the question is how would you so how would you say that has wife is a role? So
is a role, yes. Yes.
okay. So in the so you can use something similar. So let's say we said person is a class. Mary here is an individual. We can also say that John is an individual, which we should say that, but I just skipped it. And we should also say that has wife is a role. So you can remove this assertion, right? You can just say object property has wife. You can say declaration object property has wife, and that is it.
Okay. And okay, so
So
declaration and class.
so
And
we will be I think later on we will be talking about the two types of properties. One is the object property and the other one is the data property. But okay, you had a question.
no. Yes, I was asking that are these only if I are these only two? These are the only two types of.
Two or three types. So there are three types, right? So you have a again just okay, please. Let me discuss. Yeah. So you have only three types of entities. You have a class, you have property, and then there's the individual. So there are only three types, but in the property there can be two types of properties. You have the you have the object property, and then the other type of property is the data property. So object property always connects two individuals. So John, and so in this case it's John and Mary. Data property connects an individual with a literal or a constant, right? So for example, you can say that John has age 30, and now 30 is of data. 30 has the data type integer. So if you are connecting a individual with a literal, then it becomes a data property, like has age or has length, has breadth, whatever. So and has weight. So these are all data properties.
Thanks.
Okay. So any other questions? Okay, so let me just go ahead and so we'll be discussing some examples, right? Now. So again, this is just to show that all these things are related. So description logics can be converted to first order logic, and this is nothing but description logics, right? So except that this is a syntax that is more convenient for serialization. That means when you are writing this to a file, this syntax is more convenient than the symbol based syntax that we saw for description logics. Okay, so for subclass of we use this particular phrase subclass of. So woman is a subclass of person, mother is a subclass of woman, And this indicates that person, human are equivalent classes. And disjointness here is not indicated by the intersection, by the combination of intersection and the bottom. That's what you use in description logics. Here you simply say that mother and father are disjoint classes. This is like the keyword, right? It's the keyword in the OWL language or OWL language. All these are keywords, right? So there's a subclass of keyword, there's the equivalent classes keyword, and then there's a disjoint keyword. And you have similar hierarchies in properties. So you can have subproperty of has daughter is subproperty of has child, and you can also say that these two are disjoint of each other, disjoint property. Okay, so we do have the discussion on object and data. So in object property, as I mentioned, one individual is connected to or related to the other individual by this particular property. So John and Mary are related by has-wife property, and John and Mary both are individuals, right? In data property, you have an instance or an individual connected to a data value. So John has age 51, but you need to qualify it further. You need to say that 51 is of type integer. And all these data types, they are borrowed from XSD, XML data type, right? XML schema data. And other examples are has weight, has roll number, what else? Has length, has breadth, and so on. So those are the data properties, right? So you have classes, individuals, object property, and data property. Okay. So you also have the, we can also specify the domain and range. So domain and range are like the link between class and property, right? So for example, you want to specify the domain of has owner is, domain of has owner is vehicle, and the range of has owner is person. So you can use this particular keyword, object property domain, right? And object property range for has owner is person. So yeah, again, you can specify the domain and range for data properties as well. For this particular has age data property, the domain is person and the range is has age. Sorry, the range is non-native integer, right, for has age.
I have a question actually.
Yes, yes.
So when you actually declare a property, should we declare this domain and range? Like, is it mandatory to declare the domain and range of the property?
Yeah, okay. So generally, it is a good practice to define domain and range. So, for example,
Okay.
we can use reasoner can use domain and range to make some inferences, right? So, let's say you have declared something like, okay, I can write it here. So, let's say, yeah. So, object property has or work set maybe. So for work set, okay, you don't need work set has domain, let's say organization, right? Is that no employee, right? Employee. And then you have something like object property range. So I think we'll also hopefully look at these later on, but I don't mind. The range of work set is organization. And now if you say that John works at IBM, so you have works at John IBM. So from the first one and the third one, you can infer that John is an employee, right? You can automatically make this. So these are the inferred statements, right?
Okay, so in this case, then we don't have to declare John separately as a like, you don't have to declare John as an individual of
Right.
class.
So that
employee
is automatically inferred. So these are
automatically inferred. Okay.
yeah. So yeah, otherwise, yeah, you can skip these two statements and you can directly say these things, and that will be inferred. Yeah, so that's the advantage of having domain and range. But even otherwise, it's always a good practice to add domain and range for all the properties that you constructed, right, or that you want to put in. So along with this domain and range, you should also carefully think of the the characteristics. Uh, we discussed that somewhere, right? Okay, it's in the other. All the different types of role characteristics that each role can have. Something like the transitivity. Where was that? So these are the role characteristics: transitive, symmetric, asymmetric, reflexive, reflexive, functional, and inverse functional. Right. So for all, we can check for each role that we created whether any of these hold, whether any of these will be true, and then we can also add that. And adding the domain and range is also a good practice. Okay, so we can stop there. So let me just try to remember. So the domain and range, right? So we were here. So we can come back to this one tomorrow again. So I'll wrap up the whole part, the web ontology language part. This is mostly the syntax, and then we can do the modeling together, as we said. So please do install Protege tomorrow before you come for the session, and then during the session we can use this to create an ontology, and we can do it together, right? So I'll ask you for some suggestions, and you can keep suggesting it, and we can build the ontology together. Okay, so that's the plan for tomorrow, and if you have any questions, let me know and I can answer it. If not, we are done for today. Are there any questions? Okay, so I'm assuming that there are no questions, and we can stop the recording.
Yeah, I'll stop the recording now.
Sure. Thanks.